This is the first of two videos on evidence-based dentistry. In this video, I'll provide an overview and set up a clinical scenario. I will also go through some elements of research design using the Henniken-Handurdos et al. Article as an example. I'll be using a lot of terms, many of which may be unfamiliar to you. Reference to the article will help to provide a context. Evidence-based dentistry is the ability to access, summarize, and apply scientific literature to clinical situations. But it is not just about the literature. EBD is where scientific evidence, clinical expertise, and patient values, needs, and preferences meet. All three elements are necessary. One must consider the evidence, as well as the patient's perspective and one's own abilities, limitations, and preferences. All treatment decisions begin and end with the patient. Your patient may come to you with a complaint or concern, or maybe just a question, or she may exhibit signs or symptoms of disease. If the concern is a common one, or one that you routinely encounter, you may be able to address it right away. But what if it is not common or routine, if you don't have an answer? In this case, you must turn it into an answerable question, and then search for the best available evidence. You would evaluate this evidence, and then determine, together with the patient, whether it's applicable to your situation before making treatment decisions. I'm going to focus on the evidence appraisal part. Suppose that a patient tells you that she flosses but doesn't feel like she's cleaning between her teeth as well as she would like. She wants to know about interproximal brushes. Because there are so many out there, she wants help in choosing one. You don't feel comfortable making a recommendation because you're unfamiliar with the evidence on effectiveness of interproximal brushes. You tell her that you will get some information and let her know what you find out. This is the evidence pyramid, which depicts common research designs. The research design is how researchers get their data, and it is of critical importance to any investigation. The bottom half depicts primary research, research in which data are collected directly by the researcher. The top half shows secondary research designs, in which researchers study data from previously conducted investigations. The further one goes up the pyramid, the less risk there is of bias, systematic errors in data collection or interpretation. A study higher up on the pyramid is not necessarily a better study, but the design is less prone to bias. You're going to do a search of primary research, and you'll focus on studies that used an RCT design, the one with the least risk of bias. The reason that RCTs have less bias than other primary research designs is that they use a process called random assignment to place subjects in treatment conditions. This is done in such a way that all subjects in the study have the same chance of being selected into a given treatment group. Randomization assures that any differences between groups at the start of the study are due only to chance factors rather than systematic errors. You do your search and you find this article that compared a rubber bristle interdental cleaner to one with nylon bristles. What were they looking for, and what did they find? Their primary objective was to compare the two devices for gingivitis. Secondarily, they looked at their effects on dental plaque and gingival abrasion. And finally, they asked participants about their perception of the devices. Research involves the study of variables, characteristics that can take on more than one value. In this study, there was one independent variable, interdental device, with two values, rubber, denoted RBIC, and nylon, denoted IDB. There were three clinically related dependent variables, gingivitis, plaque, and gingival abrasion. These variables were all clearly defined so that other researchers would be able to replicate the results. The final dependent variables related to patient perceptions. For these, subjects answered questions using a visual analog scale. Each question included a 10-centimeter long line with negative and positive anchors. Participants responded by marking a point along the scale, which was then converted into a measurement of length from the negative anchor point. Now let's look at the research design elements included in this study. The authors provide very specific information about the research design. That's a lot of jargon to unpack, so let's look at these one at a time. First, the researchers compared rubber and nylon bristle cleaners. All subjects used both devices at the same time. Another way to have done the study would be as a crossover design, where subjects use one device and then switch to the other. This was a split-mouth design using the mandible, so subjects used one device in one mandibular quadrant and the other device in the other quadrant. The examiner who took clinical measurements did not know which quadrant was assigned to which device, and did not have access to clinical data from previous examinations. The statistician was also blinded to quadrant assignment. An ideal design uses double blinding, or masking, meaning that the subject is also blinded to assignment. Double blinding is not always possible, as in this study, where subjects could clearly tell the difference between the two devices. In an RCT, treatment assignment is done using a randomized process, eliminating the possibility of bias. For this study, both quadrants had the same likelihood of receiving the rubber-bristled device. Bias can occur when an investigator, consciously or otherwise, assigns subjects to treatment groups in such a way that the groups differ in a systematic way. For example, if a researcher in a drug trial tends to assign sicker people to the treatment group and healthier people to the control group, these two groups will differ in an important way before the study even begins, therefore allowing an alternative explanation for results. Randomization removes this potential bias. Confounding is another serious research design concern. A confound is a factor that is not part of the research design, but which influences study results. For example, if some participants in this study had periodontal disease and others didn't, but the researchers did not take periodontal disease status into account, it would be a possible confound. Random assignment helps to reduce bias, and the split mouth design addresses potential confounds by having the same subjects in both treatment conditions. Any investigation involving humans must be approved by an independent review board whose purpose is to protect the rights of subjects by assessing the relative risks and benefits of participation. This study was approved by such a board and followed good clinical practice guidelines as laid out in the International Conference on Harmonization. Establishing inclusion and exclusion criteria helps to reduce confounds. For example, subjects had to be non-smokers and of good overall health, and they could not be dental students, presumably because you know too much. While these criteria tighten up a research design by eliminating potential confounds, they also result in a decrease in generalizability of results. For example, the researchers would not be able to state with confidence that their results apply to adults over the age of 35 or to those who wear orthodontic appliances. In an ideal situation, researchers would use random sampling to acquire subjects because this process assures that all potential subjects have a chance to participate. In real life, random sampling is difficult, so typically researchers use a sample of convenience, volunteers. This study drew participants from a database of people interested in participating in clinical research and through postings. Because the purpose of research is to generalize from a sample to a population represented by the sample, one must ask how volunteers might differ from the general population and how that might affect the results. The researchers did a power analysis to determine the minimum sample size needed to detect a real difference between the two treatments, based on the primary outcome of interest, bleeding on marginal probing. A power analysis should always be done before conducting a clinical trial to ensure that the sample size is adequate. Without going into details on this process, the researchers found that they needed a minimum of 40 subjects. They recruited 44 to allow for 10% potential attrition. Once all subjects were enrolled, the study began. At the first visit, participants were instructed on the use of the devices and were then given 2 weeks to become familiar with their use. At the next visit, day 0, clinical measurements were taken, and subjects were instructed to refrain from brushing mandibular teeth. At visit 3, clinical measurements were again taken, and participants were told to use the devices as assigned. The time between these 2 visits represents the experimental phase, during which gingivitis was experimentally induced by having subjects refrain from oral hygiene behaviors. Visit 3 is when the devices were assigned to quadrants, and the treatment phase began. Clinical measurements were taken at each of the next 3 visits, and patients were asked their opinion on the devices at the final visit. Block random assignment was used to determine quadrant assignment. This is an excellent way to achieve balance in group assignment. In simple randomization, the rubber bristle device would have been randomly assigned to a quadrant in a consecutive manner, with the nylon bristle device going to the other quadrant. This would be like writing left or right on pieces of paper, placing them in a hat, and then drawing them out one at a time, returning them to the hat before drawing again. The problem with this method is that right or left is equally likely each time, so that it is very possible to end up with a lopsided assignment. As an example, the rubber bristle device could have been assigned to the left quadrant for 13 of the first 20 subjects, putting the 2 quadrants out of balance. With block randomization, the researchers assigned quadrants in blocks. Using a block size of 4, there are 6 possible ways to get 4 letters that retain the balance in the number of left and rights. These now become the pieces of paper that are drawn from the hat. Block randomization assures that a balance is attained throughout the assignment process. Subjects were given a lot of instructions to follow during the treatment phase. This provides both standardization and consistency, and reduces the number of potential confounds. For example, prohibiting the use of other interdental devices or antiseptic mouth rinses eliminates them as possible alternative explanations for study results. The researchers also included several features to enhance compliance, such as asking participants to maintain a dental calendar and by sending reminders. Subjects also returned both the toothpaste and the used interdental devices at each visit so that the level of compliance could be determined. This is a strong research design. It avoids bias, addresses many potential confounds, encourages subject compliance, and assures that there is an adequate number of subjects to have a good chance of finding real differences if they exist.